Hello, everyone. Morning.
Morning.
Good morning.
Yeah, good morning. So, let me share my screen. Okay. Oops. It seems I have to. Okay. So is that okay? I think last week, not last week, last lecture, right? We were talking about uh, multiplexing and demultiplexing with UDP and TCP, right? Still remember the difference? That's important, okay? UDP using the destination port number, TCP demultiplexing using the four tuples, source and the destination IP address and port numbers, right? That's the main difference. And after that, we go to the UDP user datagram protocol, right? I think we have mentioned this not only once, but several times, and we show an animation. Okay, let's just quickly go through that. And I think at the end of the last lecture, we mentioned um, one question, right? Still remember, if there is some bad bits or some bad bytes, right? But generally speaking, bits is okay, right? Not byte based, but bit based. If we have some bad bit or bit flip or something, right? How can we detect this error, right? Because for UDP, we cannot guarantee sending and receiving the data in order or lost or not lost. But if we receive that datagram or segment, how can we guarantee there is no error there, right? So this is something different from not in order or not received, right? This is something like received but not correct, right? This is something UDP can let you know, okay, based on the scheme that we mentioned, the checksum. Okay, so you can see here, this is a UDP segment header. We have the source port, we have the destination port, we have the length, we have the checksum, and then it's the application data. So for today, we're going to talk about checksum, this part. How can we use the checksum to identify the errors, right? To know if you receive the segment you receive is not damaged, right? Um, how can we do that using the checksum? So the goal is to detect the errors like bit flips in transited segment. So for bit flip, maybe some of you know that, but I assume that most of you may, this is your first time to hear about that. So for bit flip, let me give you some background. Okay, so you know the computer architecture, right? System, they have the different components. For networking itself, they have the different transceiver, receiver, right? They have the different hardware component, right? And for the other computer hardware, for example, CPU, memory, storage, all are based on some transistors, right? So this transistor could sometimes have a incorrect bit inside. For example, if you put, let me give you a very interesting example in high-performance computing area, because people in our area sometimes talking about the errors happening in very high height, or maybe, for example, if you put a machine in a high mountain, right, very close to the galaxy, then sometimes the bit flip rate would be much higher than if you put the machine in the normal height area, right? So the reason is that there are a lot of rays from the galaxy, different X-rays. They have the different particles to stock your hardware, and this will result in some bit flip in your hardware. This is not like a story. This is the truth, right? So because the atmosphere can help you to protect the people, protect the hardware, right? So if someday the atmosphere is broken or something is not there, and then the particle will be much stronger than before. The hardware could be has a very high failure rate. So this is a one situation. So another situation, maybe that people are NASA are sending the device to Mars, to some different different areas or different regions in the galaxy, right? So they have to make sure that the device they send there will not be affected by different storms or a lot of things there. So the resilience and the reliability sometimes is a very important thing. But this is something not exactly related to our networking. But my point is here, for most of the computer hardware or device, it can have the bit flips, right? The bit sometimes it can be flipped from 0 to 1, from 1 to 0, right? We can manually flip that, but sometimes it's accidentally be flipped due to some accidents. So how can we detect this kind of the error or bits is very important for the reliability of the computer system. Okay, but here we only focus on the protocol itself. We have the different protection scheme. For example, people are using the ECC, error correction code, in the memory. So maybe that in the GPU memory or CPU memory, you can manually close or enable ECC. Sometimes you have user privilege, right? After you enable or disable the ECC, the performance, energy consumption, a lot of things could be totally different, because ECC is a computation unit in your memory, right? It needs to help you detect if there is some error happening in the memory. If there is some error, that error should be corrected based on the ECC scheme. Many research, many topics in this area, but generally speaking, we should have the different protection scheme from the different computer system levels. So here we are talking about the protocol level, right? As I mentioned, in the ECC hardware itself, that's the hardware level, right? It first help you to protect something, but there will always some error can skip from the hardware protection to the application level or to the protocol level. So that's why in the application level, we also need to have some protection. For example, you need to checkpoint, right? If some software running in your computer and it's frequently or from time to time to save some data, and if it has something wrong happened, it just reload the data. That's also a protection, right? So here we are talking about the UDP checksum. That's a very simple, straightforward, but could be used in different areas. Checksum is not only limited in the UDP or network protocol. It can be used in a lot of places. So actually ECC is a checksum as well, right? It's a checksum, but be integrated in the hardware itself. It's still the checksum. Okay, so checksum is a very important and widely used methodology. So here is just a simple, straightforward example to let you know what is a checksum. So if you transmitted some value, right, between the sender and the receiver, the first value is 5, the second value is 6, the sum should be 11, right? But after you receive the data, let's just do a very, not a realistic assumption. The 5 flip to 4, right? Or some error happened, 5 changed to 4. And then you receive the value 4 and 6, okay? But you still receive the checksum value or sum value, right, of 11. Then you can easily verify if 4 plus 6 equal to 11. If it's not, means that something wrong happen. And now we assume that, later we will talk about it, but now we assume that the sum would be corrected, would be correct, okay? Because we have a lot of values and we only have a one checksum here. So if some error happened, mostly or most frequently it would be happened to the value themselves instead of a checksum. But if the checksum has some problem, what can we do, right? This is a problem or question we will talk about later. But now we assume that the checksum or this sum would be always correct. So this sum would help you to know if there would be something wrong with the value itself, right? But maybe some of you also think about, okay, so if I receive a value from 5 to 4, but receive another value from 6 to 7, the sum is still 11, right? As this case, even if you receive two erroneous values, the sum or checksum still correct or still be satisfied. You cannot identify the error, right? So how should we do? Okay, so this is like a cancel out, right? So the error just cancel out with each other and you cannot identify that. So we will talk about it later. But here, just give you a quick idea. I talk many background knowledge because I think this is not only related to the computer networks. You will see the checksum utilization or usage in different scenarios, and also error is not the only issue in the network, in a network cause, right? It can be in the hypervisor computing, can be in hardware, can be in a lot of places, okay, in CS. So here is just a demonstration, right, about the checksum to verify the correctness. Okay, it's not equal means that error happened, right? So the sender just treats the contents of the UDP segment, including UDP header fields and IP addresses, as a sequence of 16-bit integers. So they don't care anything you send, if it's a video, radio, or audio, or anything, right? Just treat every data as the 16-bit integers. And they can do the checksum, okay? Because they treat as an integer, they can do the sum, right? Using the summation calculation, right? The checksum is just addition once complete sum of segment content. Just add every 16-bit integers together to get the sum, okay? The checksum value put into the UDP checksum field, as we mentioned before, right? So there is a source, IP, destination IP, checksum, and the length, right? So you can know the segment information based on these values or this information. And the receive just compute the checksum of received segment. After you receive the segment, you compute the checksum, recompute the checksum. Okay, you recompute the checksum based on the data you received, and compare the recomputed checksum with your received checksum. If they are equal, means mostly or highly probably there's no error happen. Okay, so but I also talk about that there is some cancellation, some cases, but let's just say that mostly it's correct. Okay, so the check if compute is the checksum equal to checksum field value, no equal error detected, equal no error detected, but maybe errors nonetheless, right, or more later, right? We will talk about that later. Just I mentioned cancellation or checksum itself would have some problem, right? So as you saying that you don't recompute the checksum, you add the checksum to the data values and make sure the result is a 0. That's why checksum is a once complete. Okay, so yes, this is how you calculate the you recompute the checksum and you just reduct these two values, right? Or means that add the value to the checksum, it's the same, but a different calculation orders or methods, but the idea is that you computed one checksum from the data you received and compare with the checksum you received, right? No matter how you do that, you can just add all the values you received and compare them, or just add the value to the checksum you received. That's the same, right? That's a different calculation method. But the idea from the high level is you recalculate the another checksum based on all the value received and you compare them, right? How you implement that, that's the same, maybe just as you mentioned, right? So you just add the values to the checksum and see if it's equal to 0. That's the same, right? But my point is that the idea is you need to compare the received checksum and you calculated checksum, okay? That's the idea, no matter how you implement that. So you add the data to the checksum you receive. That's maybe a better implementation, right? But from a mathematical point of view, they're the same. Okay. So let's see how we calculate the checksum. I mean, in the center side, right? So you need to put the checksum in the segment, okay? And how you calculate the checksum? For example, we have the 16-bit integers, and we want to add them together, and we just do a binary based calculation, right? Adding them together, addition, 0 plus 1 is 1, right? And then 1 plus 0 is 1, 1 plus 1 is 0, but you need to put the 1 here, right? Just carry to the more significant bit. You just do this until the most significant bit, right? But note here, when adding numbers are carried out from the most significant bit needs to be added to the result, okay? So for example, here, if we have you have the carry out from the most significant bit. We just, because this is the 16 integers, right? We don't have any other bit here. So we just put this bit to the end, okay? We just put this one to the end, and you add 1 into the 1, 1, and it comes to, becomes to 1, 0, 0, okay? This is just a small trick here. So to let you still use 16-bit integers to store the checksum, okay? And this is just a two 16-bit integers. Also, you can add more, right? You add all the values in the segment and calculate the final checksum. Okay, so this is a final checksum you will get. Okay, and so here I think it's just as a animation, right? So even though numbers have changed, bit flips, no change in checksum, right? So the idea is that you use a one value to detect or to identify if there is some error happened in all the values in the segment. Okay, so I think there is no mention about, in this slide, there is no mention about how you deal with if there is some error happened in the checksum itself. Okay, but generally speaking, we'll mention that later. So there is some duplication scheme. So how you can make sure the checksum is correct, then you can just duplicate, right? If you don't know how to detect some value, if it's correct or not, right? For example, I give you a value, I give you a paper, each paper will have a value, right? Maybe some paper is just broken. How you can protect the information? You just copy the paper for several times, different duplicates, right? And then you just, once you receive the data, you just compare across the different duplications, right? And if there's always every piece of the copy are the same, means that no error happened in the checksum itself, right? So this is something the slide doesn't mention, but we will mention, I think, later. Okay. So here is a quick summary about UDP. There is UDP protocol is no freeze protocol. The segments may be lost or delivered out of order, but the best effort service is send and hope for the best, right? So just you hope the transfer will be no problem, okay? But if you receive the segment, the checksum will help you to protect that, right? So UDP has its process. So no setup handshaking needed, as we mentioned, can function when network service is compromised, and it can help with the reliability checksum. Can help with that, right? So it's not always guaranteed with the segment delivered, but can help with the reliability, right? Okay, so I think UDP, to be honest, I think it's not very difficult or complicated protocol. Straightforward, right? Send a segment, receive a segment, right? Check something here. But I think for the TCP, it's more complicated than this because we have to make sure that every piece of the segment would be delivered and in order. Okay, that's something you need to think about. How can you guarantee if a segment is not received and how you can respond? Okay, if one segment received and if you want to make sure the order, how you can do that? Maybe you, as we watched the video before, maybe you add number for the sequence there, right? Or you just make all the delivery will be in order. So how you should do, right? So this is a protocol we will talk about later, but you can, during the meantime, you can think about that, right? Because we have already introduced the UDP. If we want to make sure that the UDP to be similar to TCP, how you can change the UDP protocol, right? To be a similar to something like a TCP requirement, right? But actually we will give the detail about TCP, but how you can change UDP, right? To make it maybe similar to TCP. We do a handshaking of that, how you can make sure the delivery in order or segment will be always delivered. So yeah, think about that. We can talk about the contents during the meantime, okay? So UDP can build application functionality on the top of a UDP application level, like HTTP3, but as we mentioned, it's not very widely used. Okay. So let's go to the TCP. So first is the principle of the reliable transfer. The principle of reliable transfer is that you have the different send and receive protocol, and you can have different reliable or not reliable channels, right? So we just do abstraction. So here is that we have the reliable sender side, we have the reliable data transfer protocol, okay, from the application layer to transport layer. And we also, from the receiver side, we also have the reliable transfer protocol, okay? But the channel or the lower layer could be unreliable, okay? From the transport to network, they can be unreliable channels. Okay, the reliable service um, sometimes may not be possible, right? So you have to make sure that even your transport and application are based on the unreliable channel, right? How you can guarantee the transport layer and application layer still be 100% reliable? That's a question, right? You cannot assume that the lower layer is reliable. It's just like I just give an example for the computer architecture, right? If some bit flips in your memory, if some bit flips in your CPU, right, calculation unit, what happened, right? So they can protect it first, but if they cannot protect, you need to do something, right? In our scientific computing, always we want to check some value, right? If it is for example, in the some physical simulation of phenomena simulation, they can check the energy, right? So if this is the energy doesn't look very make sense, that means the computation or hardware could have some problem, right? But this bring your domain knowledge to the verification, right? But generally speaking, how you can verify the correctness of the application. Similarly here, how you can guarantee the data transfer back and forth are correct, right? Based on the assumption that the transport below layer, network layer are not reliable, okay? So here's the principle. The complex of reliable data transfer protocol will depend strongly on characteristics of unreliable channel, loss, scrap, reorder of the data, right? So if you propose a reliable data transfer protocol, that protocol needs to has no assumption about the lower layer protocol. Okay, it just assumes that anything could happen. Data loss, data corrupted in not in a good order, right? But how you can develop the protocol here. Okay, and okay, so here's a good note. So the sender and receiver even do not know the state of the other part, right? For example, if the message was received, you don't know. You have to develop a protocol to know that, right? But every side is just independent with each other. You don't know that, right? And unless you have the communication, you develop a protocol to communicate with each other, right? Otherwise, you don't know this information, okay? So let's see, this is a diagram to, we will use it for many times in the next tens of the slides, okay? So this figure you have to remember because we will use that in um, next several lectures. So here, from the sender side, you have the reliable data transfer protocol, send, okay? It sends the data and it passed the data to a packet and to the UDT. UDT is the unreliable data transfer protocol, right? This is something we just mentioned, unreliable channel here. Oh, I should change to a later point. Otherwise, you cannot see my mouse here. So, okay, so here is a UDT sender, right? Through the unreliable channel to the reliable data receive, okay? And deliver the data to the application level. So the sender side implementation of the reliable data transfer protocol for the reliable data transfer protocol, okay? And receiver side implementation of the reliable data transfer protocol for this layer, but we have the unreliable channel here, okay? So this is you need to remember RDT means what and UDT means what. Okay, so RDT sender call from above, for example, application level, pass data to deliver to receiver up layer. And the UDT sender is just called by UDT sender called by RDT, right? Because this is a lower layer, right, protocol called by the RDT to transfer packet over the unreliable channel to receiver. And the RDT receiver, I just explained this is the note here. Okay, I don't want to go through that. I just explained. And this is a bi-directional communication over unreliable channel. Okay, so this is a bi-directional communication, and this is the data. This is the packet. You should. I think we mentioned that from the application level we use each level or each layer will have the different unit of the data, right? For the application level, we just use data and the datagram, but for the transport layer, we use a packet because the different protocols will segment the data to the packets, right? So the reliable data transfer, this is a something you need to know. Okay, so we will incrementally implement develop a sender and receiver side of reliable data transfer protocol, RDT. Consider only unidirectional data transfer, but the control information will flow both directions. So for the simplicity, here is our assumption, right? So every time the data only transfer in one direction, but the control flow could be flow in the different directions, okay? And here, I think we need to introduce a new concept, maybe little bit difficult for you if you don't hear this before. So for the next tens of slides, we will use finite state machines to specify the sender and the receiver. So what is finite state machines? So FSM. So this is a very important research or concept um, area. I know some of the professors are working for this area for their whole life, right? So finite state machine could be very useful in many application or scenarios. So what is a finite state machine? So just if I just use one sentence is that the state, right? So you can see here there are two states, okay? So the state would be changed only depending on the event or the finite number of the event happening from this state to that state, okay? So which means that there are only few numbers of event would cause the machine from one state to change to another state. Okay, so the benefit is that you don't need to think about a large design space. For example, vending machine. So vending machine, I think, is a very famous or the simplest case to think about the FSM. Okay, finite state machine. So that machine only have the you can use a vending machine, but you input the number there, right? So different number just triggers the machine from one state to another state, right? The state is in the finite state, and the one state change to another state, it just depends on the limited number of the conditions, okay? So we can plot our protocols, reliable data transfer protocols using the finite state machine FSM. Um, this important technique, okay? So if you don't quite understand here, I think it's fine. We will use some example to let you know how we can uh, leverage the FSM to deliver to develop our reliable data transfer protocol. Okay, but in general, that we have the different state in the protocol itself, and there are some different conditions to trigger the states to change from one to another. Okay, that's a general high level idea why we want to use the FSM here. Okay, so let me continue. So let's see the first reliable transfer protocol. That's a very simple or straightforward protocol. So we call it 1.0. Okay, so this is underlying the channel perfectly reliable. Okay, means that no bit errors, no loss of packets. So you can think about the loss of packets and bit errors are in the different granularity, right? So for the loss of packets means that the total packet is just gone, just lost, right? But bit error means that you receive the packet, but it's some bit is erroneous, right? Or some bit is flipped, right? So the data is not complete. But loss of packets means that the data is completely lost. Okay, so this slight different. So separate FSM for sender and receiver. So the sender sends the data into underlying channel. The receiver reads the data from underlying channel. So we can plot the FSM for the sender and receivers, right? Two FSM here, finite state machine. So for sender side, you wait for call from above, right, from application layer. And what kind of the condition can trigger is a state chain, right? So here is just the state change would be based on the reliable data transfer protocol send the data, right? If the above application, right? Let's say the above, you always mention above is application, right? From above application call this RDT send protocol, this protocol send, right, data, and this finite FSM status will change, right? Will change. And what is specifically in the RDT send data? So it will make a packet and it will use the UDT, is the unreliable data transfer protocol, to send the packet through uh, the link, right, or through the lower layers, right? So this is a sender side. But what about the receiver side? So the receiver side also waits the call from below, right? Below, from the physical link or from the data link layer, right? And then after that, if you what will trigger is a state change. So if you receive the data, the packet, right? It's not data, receive the packet, and you extract the packet to a data, right? And then deliver the data to application, right? To above, okay? So is that clear here? So for the different sides, there is no communication so far, right? Different sides just have the different states and the different trigger condition, right? For sender side, it waits a call from above, and with which condition will trigger its state change is just send the data. Okay, after it gets the call from the above, it will send the data, package the data, and send the packet through the UDT protocol. And from the receiver side, it just receives the packet and extract the packet to data and sends the data, deliver the data to the application level. Okay, both sides has the separate FSMs here. Okay, that's easy because you don't need to think about the reliability problem. You always have the UDT send and the RDT receive to be very reliable, right? So channel are totally reliable. So you don't need to handle about the resender things or packet loss or anything else, right? Just send and receive. That's what we have done in the local laptop in the demonstration, right? We assume all the packet would be delivered and received. But this is an ideal case, right? It's not, just I mentioned, it's not always be true. Underlying channel may flip bits in the packet, right? As I mentioned. So, okay. So even if we are, okay, so here's something I didn't mention. So even if we don't have the extreme case, we put the machine in a very high mountain or something, galaxy, if I forgot about this, even if we are in the normal condition, not extreme case, then the error still happen because you have a lot of components. Even if one hardware component has one bit flip, the data would be corrupted, right? So you can think about for the whole laptop, you are sitting in front of a laptop or desktop, right? You have millions of components in the computer hardware or networking, right? Even if one bit is flipped, the data would be corrupted. You can think about the chance, right? So even bit flip would be very low chance. You think about a large number of components hardware in your laptop, desktop, then the chance would not be very low, right? It could be low, but not very low, sometimes bit flip. So we need to protect this case, right? Prevent this case happening or affecting our application. So as we mentioned, the checksum, internet checksum to detect bit flips. And the question is that how to recover from the errors. You detect something, right? I didn't mention that UDT can only help you to detect the errors. After you detect errors, what should you do? You just report the errors, right? After you report the errors, UDT will not help you to do anything else to correct the error, because it just tell you, okay, if you quick search in the Google, you will see that a lot of people sending the error message saying that the UDT protocol has a error because of a bad checksum. Okay, it's just a report a bad checksum. It doesn't do anything to correct that. So if you think about the protection, it has detection and the correction, right? UDT only think about detection based on the checksum. Then what about correction, right? How we can recover from error? That's something the new protocol RDT 2.1 needs to think about. You cannot just say that you detect something, then I don't do anything, right? But I must do something because this is a reliable data transfer protocol, right? You have to recover something. Then the easiest way, maybe you can think about just resend, right? I received something bad. For example, you order something from Amazon, the packet is broken, right? The item is damaged. How you can do that? You cannot fix by yourself, right? Maybe some of you can fix by yourself, but generally speaking, you just tell Amazon and ask them to resend the packet to you again, right? But this is something like a protocol. You call the customer make sure that your item is broken and resend that packet to you, or just refund the credit to you, right? But if you want to get the packet, definitely you want to resend, right? So that's the protocol, right? You talk to the customer service. So here for the RDT 2.0, we also need to have such a protocol, right? To guarantee even if you detect the error, you can still receive the correct packet, okay? So the underlying channel may be flipping packets is something we mentioned that. So how we can recover from errors? So generally speaking, we will have the acknowledgements. If some of you may remember the video we played in, I think in last month maybe, right? At the first few lectures about the history of internet, we play a video for the pigeons sending the mail, sending the letters, right? Still remember that video, right? We have to send the acknowledgement, right? We have to let the receiver know that, let the sender know that if I have received or not received, if my received data is corrupted or not corrupted, that means we need to send acknowledgements explicitly to tell the sender that the packets had been received okay or not okay, right? If it's not okay, it's a negative acknowledgement. If it's okay, it's acknowledgement. ACKS and NAKS. So this is the two abbreviations you should remember. We will see that many times later. So don't forget about the ACKS, means acknowledgement, means you receive the packets correctly, no corrupted. Not no corrupted, but receive the data, and negative acknowledgement means you haven't received the data or your packet has some error, okay? So the sender would retransit the packet on receipt of NAK, right? Not a negative acknowledgement. Okay, so what about if packet is broken or something, right? So the principle here is that you just stop and wait. The sender send one packet until receive the response, right? Because you want to guarantee there is no packet lost. The packet could be received in order, right? So this is a principle, not like a UDP, you just send, and receive, right? So it doesn't care about the order, it doesn't care about the packet loss. But for the reliable data transfer protocol, it has to send and wait, and send and wait, right? So this is like a procedure. So how about the FSM specifications? We can plot here. Similar to the RDT 1.0, right? So we have another state because we send and we need to wait, right? So that means we have two states here. Wait for call from above, wait for acknowledgements or negative acknowledgements, right? This is sender part. What about receiver part? Similar, right? Let's first finish the sender part. So sender part, what triggers the states of the FSM change or trigger? Similarly, the RDT sends the data, right? So here is a sorry, okay, here. So here is the RDT send data, right? Triggers the states to change from wait from above to wait for the acknowledgement or negative acknowledgement, ACK or NAK, right? So this triggers the state change, right? And what triggers the state change back? After you receive the acknowledgements or negative acknowledgements, and you just receive the packet, still remember this RDT receive packet. If you don't remember, let's go back to this slides. So this is the same thing, right? RDT receive packet is extracts the packet to data, deliver the data to the application layer. Okay, so this is something we have already mentioned actually, but if you don't remember, just go back to the previous slides. So what triggers the state change back? It's receive, the RDT receives the packet, and if you expand this function, it will be extract the data and pass the data back to the application, right? And also you need to make sure you receive the acknowledgement okay, then trigger this status. Okay, if you receive the NAK, how the status will change? I think I should ask you a question. So here you can see that send the data, right? Wait and wait. This status just receive the data acknowledgement and just unpack the data pass to the application. So what about if I receive the packet but is the NAK, negative acknowledgement? How you should plot the FSM? How you should do that? Yes, that's a loop back to RDT send. Okay, but actually that's not a loop back to RDT send is a status change condition, right? You need to have a loop, but this loop would be here. Okay, here is just a loop because you will not go to the state, wait for the call. You still wait here, right? The state actually is not changed, right? You still wait because you don't want to go to the further state, right? So this state just a change to itself, but the condition is that you receive the receive packet and is ANK, right? And then you just RDT send again, right? So this is a condition, but you still wait here because you need to wait until the acknowledgement received, then change to another state. So the state would not be changed, but just a looping here and our UDT's resend, actually not resend, but just send, right? Because send and resend is the same function, okay? So this is a FSM specification for the sender part. What about resender part? What about the receiver part? So receiver part is, I think is pretty straightforward. If you receive the data, right? The data, if it's okay, you just send the no corrupted, right? And receive the packet. If it's corrupted, you send the NAK, right? It's just simple, right? You receive the packet. If it's not good, if it's not complete, you just report corrupt, right? And send the NAK, right? And if you receive the packet and no corrupt, you just reply the no corrupt, right, acknowledgement, and then you just unpackage the packet and pass that to your application, right? So for the detailed function here, you just extract the data, pass the data, send the acknowledgement. And for this one, if it's a corrupt, it's just a UDT send NAK, right? Let me check if there is a problem. Yes. Okay, thanks, Andrew. Yeah, good answer, actually, I think. Yeah. So understand these figures, I think these figures it will become more and more complicated. So if you don't understand the first several figures, then you will be confused for the future one. So I can quickly show you how complicated the future one will be, right? So if you look at the next several, it will be very complicated like this way, right? We don't need to remember every detail, but if you don't understand how the FSM would be changed, would be from one status to another state, it will be difficult to understand for the future uh, specification, right? So here is a very straightforward. Let's just repeat that and let's end today's lecture. So center part is just two states, right? From wait above to wait acknowledgement or negative acknowledgement, right? The change state is just send the data and receive the data if it's okay. If it's not okay, just loop here back to itself, okay? For receiver side, actually it's always to itself, right? Wait until a call from above, and then it has a corrupted report or the non-corrupted report detailing for the acknowledgement or negative acknowledgement, right? And this is something there is no communication. For the next lecture, we will talk about how to link these two FSM, right? So they're totally independent, right? This part, maybe some of you guess that it needs to have some connection between the sender and the receiver, but let's talk about that next lecture. Okay, so but I suggest that you look specifically into the FSM contents is here and understand that. Otherwise, for the next few slides or the lectures, you will be kind of confused about what we plot here, right? You see a lot of lines, arrows, but you will be confused. So I suggest that you understand this RDT 0 and 1.0, right? These two FSM specification. This is quite easy. After you understand here, I believe you will understand the later part. Okay. So yeah, I think that's it for today's lecture. Yeah. Any question? Okay, yeah. So thank you everyone to attend that, and see you on Friday. Okay, just review the slides we talked about today, because based on my understanding, this could be the most kind of difficult part you face in the course so far, right? Just to understand the protocol here. Okay, thank you everyone. Yeah, see you on Friday.